Okay, let's talk about the first past paper, all right? The
Yeah, sure.
W41, all right?
Yeah, sure. Just give me a moment to like prepare my past paper out here.
Okay.
So we start with paper 6. Is this paper?
Paper 6, paper 4.
Okay.
Tell me when you are ready.
Yeah, sure.
Okay, do you have this paper with you right now?
Yeah, I do. I'm just finding it. Wait, actually, I don't. I only have the May June one for 2024. I don't have October November.
Hang on now.
Yeah.
I thought I sent this document to your mom.
Yeah, she received it, but didn't print it out. So.
Oh,
Yeah.
okay. Which paper do you have right now? It's okay. I have all the papers. Which paper do you have right now?
Yeah, right now I have the May June, like all of the May June part, and yeah, for 2024.
Okay, so 2024 May June.
Yeah.
Do you have paper 41 with you right now?
Yeah, I do.
Okay, then it's okay. I have all the papers. Then I'll just use the paper that you have currently. All right.
So for the October November thing, I could do it on my iPad, like with my Apple Pen, and all. I could just download it.
Okay, sure. No worries. Okay, so you mentioned that you have this with you, right? Is it?
Yeah, that's right.
Okay. You mean printed document or what?
Yeah, it is. It's like a physical past paper. Like I bought it online.
And have you already tried this out, or is it still empty?
It's still empty actually. Haven't tried
Okay.
it out. Yeah.
Then let's do this together. All right.
Okay.
Okay. So today, let's look at this. At rest. Did you know that whenever you see the word at rest, the initial velocity must be 0? Are you okay with that?
Yeah, I know.
And now, when the ball is falling, right? Can you actually tell me what are the forces acting onto the ball?
Yeah, so when it's falling, the only force acting on the ball is its force of gravity, its weight.
Okay, so mg is
Yeah.
acting on this ball. Apart from mg, is there any other forces?
It's air resistance that opposes its motion.
We don't call that air resistance because you are in the oil. So let's just call that friction or resistance. Are you okay?
Okay.
Or maybe you can call it oil resistance if you want. All right.
Okay.
And now, in the process of falling down, did you know that your weight is always a constant force?
Yeah, I do know that.
And what do you think about friction? Is the friction a constant force or what?
No, friction, no, it's not constant.
Then, could you give me more details if that's constant?
Like, why is it not constant?
And then what will happen to it if it is not constant? Will it increase or decrease or whatever? Please tell me more.
So,
Will
wait, what's your question actually?
will friction increase or decrease? Okay, you choose one. Increase or decrease?
In this case, it would decrease.
It will decrease. No, you are wrong. Actually, it will increase. Did you know why? Because when your velocity gets higher and higher, your friction will get, larger and larger. All right.
Okay.
And did you know that? Okay, for example, let's say you are not moving. There's no wind blowing to your face.
Yeah.
And did you know that the so-called wind is basically air resistance? Did you know that?
Yeah, I do know. Yeah.
Okay. And when you are running, right? Okay, when you are running, you feel like, oh, there's some wind blowing through my face, isn't it?
Yeah, true.
And the faster you run, right? The faster you run, the greater the wind to blow your hair, isn't it?
Yeah, that's true.
Okay, this is what we are talking about today. Friction will increase when your velocity gets higher. Is that fine?
Yeah, I understand.
Okay, good. Okay, so let's talk about this. Have you ever heard of terminal velocity?
Yeah, I do.
What is terminal velocity? Could you please tell me?
Yeah, sure. So basically, it's like acceleration with free fall, and like when your weight equals to like its air resistance, then there will be no resultant force. And when there's like no resultant force, there's like no acceleration. So that is when like the ball would be traveling at constant velocity, which is terminal velocity.
Good job. And
Yeah.
one more thing to add on is terminal velocity is the maximum velocity.
Okay.
Okay, good job. I love it. Okay, so should I give you 1 minute? You try out this page or what? I don't know. You tell me
Yeah.
how can I help you,
Okay.
all right?
Okay, sure.
Like seriously, today is the first day that we meet, so you have to tell me how can I help you to maximize your performance, all right?
Okay, sure.
Tell me when you're done. Huh?
Yeah, sure. Yeah, I done for both questions already.
Okay, so you know that acceleration is very easy, right? The change in velocity divided by time. Are you okay?
Yeah, that's right.
And B-boy is so easy, lah. Okay, I can just skip like F equal to ma. All right.
Yeah,
Did you know
okay.
that F equal to ma? This one must be the net force. It must be
Oh
the net
yeah.
force.
Yeah, I know. Yeah.
So just a quick review. Let's say I don't know,
Okay.
5 Newton, 8 Newton, 2 kg. Can you help me to find the acceleration right now?
Okay. It's 0.15.
0.15. And could you please tell me your unit?
It's meter per second square.
0.15 meter per second square. Are you sure? 0.15 meter per second square. Is that true? I don't think so. That is 1.5, right? 1.5 or 0.15?
I got 0.15 actually.
Oh, okay, never mind. Is this your working? Have a look. Your net force is 8 Newton minus 5 Newton, and then your mass is 2 kg. So 3 equal to 2 times A. So A is 3 divided by 2, which is 1.5.
No, that's not how I did it.
Oh no.
Yeah.
Okay, fine. This is the correct way. Could you please learn it this way? Thank you.
Yeah, sure.
I give you 1 minute. Quickly jot it down.
Well, what can I do it like 5 plus 8 over 2 percent?
You are so clever. This is what I'm going to tell you right now. If you have done this one, can I change the question right now? I'm going to erase this. I'm going to tell you that 5 Newton is exactly the same way as 8 Newton right now. In that case, the two forces are friends, they are heading to the same direction. Then only you are going to tell me 8 plus 5 because they are friends, they are friends. Are you okay?
Oh, I got it. Yeah, I got it.
Okay. Quickly jot it down. Thank you. So it has something to do with direction. Is that fine?
Yeah, it's fine. So it's for opposite, so I gotta like minus it.
Yes, because when they are enemies, they try to kill each other, Isn't
Oh,
it?
now I got it. Yeah, I got it. What is 0.5 now? Yeah, thanks.
Okay, so make sure you have got
Yeah.
both answer correctly. Then I can move on. All right.
Yeah, you can move on actually.
Okay. Now this is velocity time graph, right?
Yeah.
Could you please tell me what is the area under velocity time graph? And then what is the gradient of the velocity time graph?
So gradient would be the acceleration for velocity.
So
For
clever. And then another one?
area under graph is basically like change of velocity over change in time.
The area is change in velocity over change in time. Is that true?
No.
No, I don't think so. That is the change in velocity multiplied by the time, all right?
Okay.
And what is that? When you have change in velocity multiplied by time, what is that? That is displacement, all right?
All right. Okay.
Okay, wait a minute, just to be sure. The area under velocity time graph is not change in velocity over change in time. This is wrong. It should be
Okay.
change in velocity multiplied by the change in time, which is basically displacement. All right.
All right. I got it.
I think you know what is a tangent, right?
Yes.
Did you know that tangent has to touch the curve at exactly one point?
Oh yeah, I do know that. Yeah.
Okay. And did you know the gradient? I mean, could you please tell me the gradient formula, please?
Yeah. So it's like m equals to y2 minus y1 over x2 minus x.
Perfect. Okay, so I think you can do this now. And now you see, they are going to ask you what happens to the acceleration, right?
Yeah, that's right.
This is exactly what we discussed just now. Let's have a look at this. Okay, let's talk about this falling ball in the oil. Could you please tell me which force is basically larger? Is it weight or friction?
It's weight.
So clever. That is why the ball is moving downward. And now let's talk about math. Do you agree math is something constant today?
Yeah, I do agree. Yes.
Do you agree that G is always a constant 9.8?
Yeah, that's right.
And just now, according to what we have discussed, do you think friction is going to increase or decrease?
It's going to increase.
So clever. As a result, by using your powerful math today, your mathematics skill, could you please tell me a friction is going to increase or decrease?
For acceleration.
Yes.
So like acceleration will increase because your friction increases.
Wrong one.
Oh,
It will decrease. Okay, I'm going to tell you this. Let us get some lucky numbers, shall we?
yeah, sure.
13 minus 8 equal to 5. Are you happy?
Yeah.
And we mentioned friction will increase, right?
Yes.
So can I say that 8 maybe increase to 9? Can I say that?
I mean, yeah, you could say that.
Yeah, 8 increase to 9. You get my point, right? So 5 will become what now?
It will be 4.
Okay, so 5 to 4. Do you think this is increase or decrease, by the way?
It's decreasing.
Good job. Okay, now jot it down. Thank you.
Okay. But I thought initially you said like friction will increase when velocity gets higher.
Yes, I said velocity gets higher, but I didn't say that acceleration will do what, right?
Acceleration and velocity, they are different.
Yes, of course.
I see.
Velocity is like how fast you are moving. Acceleration is like, are you going to change your speed now? Are you going to change your speed now? And that's acceleration. Are you okay?
Yep.
You give me a lot. I mean, later on, at the end of the day, the ball is moving so fast, right?
Yeah, true.
So velocity is very high, right? Isn't it? At the end of the day, all right? At the end of the process.
Yeah, that's right.
But at that moment, you are already moving so fast. So if people ask you, dear Bob, are you going to increase your speed now? Then what are you going to reply to me?
Yeah, I am
You are,
going to increase it.
no, you are going to say that no, I have already reached my maximum speed, so I'm not going to increase anymore. Okay, I'm not going to increase my speed anymore. I have already reached my maximum speed, by the way. Okay,
Okay.
so that is why acceleration will be almost zero. All right.
Okay.
So I can tell you, you are not alone. Please do not believe that when velocity is high, acceleration must be high. That is a totally wrong concept. Okay?
Okay.
I repeat, just because velocity is high, it doesn't mean acceleration should be high, you know. This is a very wrong concept. Please throw it away. All right?
Okay. So they're inversely proportional?
No, 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 no. Okay, please understand the story. Velocity is like how fast you're moving. Is that clear?
Yeah, that's clear. And acceleration, like you're changing the speed.
Acceleration is like, are you going to change your speed? Are you going to change it? If you are going to maintain a very high speed, you are going to tell people like, no, I'm not going to change my speed anymore. I have reached my terminal velocity. I have reached my maximum velocity, you know? Ah.
Okay, I got it.
Then just now, do you still remember when I said that terminal velocity is maximum velocity?
Yep, that's right.
And you are the one who told me acceleration is zero, you know?
Okay. Yeah, that's right.
You get that point, right? A velocity is maximum, acceleration is zero, okay?
Yep, I remember.
Okay.
Yeah, we can move on.
Okay. And this one, if you see the mark scheme, they are quite generous. Out of so many points, out of 6 points, they only want student to mention 4 of them. Then you can get a maximum marks, all right?
I see. Do you mind if I could try this part first?
Of course, please try it first.
All right. Yeah, I'm done with it, but like, do you Like for CI, like
Hmm.
do I have to like read out my answer or
Or maybe in other words, you can tell me which point that you have got it. That's
oh, okay.
that's faster.
Like the first point, acceleration decreases because I said the ball is decelerating.
Okay, and then
And then I said that its downward resultant force is greater than outward force. So I think it's at the fourth point, resultant force downwards decrease.
okay. So you mentioned that the resultant force decreasing, is decreasing.
Actually, I did not say the resultant force decreases. I said that the downward resultant force is greater than the upward force.
Then you didn't get that point. Did you know why?
No.
Because you see, first and foremost, they have put a bracket here, right?
Yeah.
So to be fair, when they put a bracket, it means something like this is actually optional. You mention downwards or not, I don't care.
Okay.
So what they really want student to answer is the resultant force is decreasing. Okay, now let's have a look at this. Okay, your resultant force is this whole thing, right?
Yeah.
So when your friction increasing, do you think your net force is actually decreasing? The whole thing is decreasing. Agree?
Yeah.
This is the point. They want student to mention that. Okay, they want student to mention that your resultant force is actually decreasing.
Okay.
Mm-mm.
Wait, but why would resultant force decrease then?
Oh, math. Just now it was 13 minus 8. Right now it was 13 minus 9. Do you think the whole thing is actually decreasing?
Well, yeah, it is.
like isn't it? I proved to you. This is 5. This is 4. Do you think A is decreasing? The net force is decreasing?
Yeah,
Yes,
it is
right?
decreasing.
Okay.
What does actually resultant force means actually?
Resultant force meaning that the final force due to all the forces. Are you okay?
Okay, got it.
Because you have so many forces today, right? You have the weight pulling you down, you have the friction pushing you up. So the resultant force is known as net force, which is already the final force, the final force. Are you okay?
Yeah, I got it.
Mm-mm.
The second point, right, where they said acceleration decreases to zero at approximately 0.03 seconds. Like, I don't see
Mm-mm.
that acceleration decreases to zero.
Okay, because you see, did you still remember that acceleration is the gradient of this graph?
Yeah, I remember.
Like starting from where onwards, it seems like your gradient is basically zero. Like starting
I
from where, it seems like starting from 0.03 onwards, your gradient is zero, right? Isn't it?
Yeah, I see that now.
Okay, this is what I mean. And in fact, I need to tell you once again, everything
Yeah,
within the bracket is something optional.
yeah, I remember.
Meaning that for you, it is actually very good enough that you mentioned acceleration will decrease until zero. You already get that point. You don't even have to mention at approximately 0.03 second. No need, no need.
Okay. Wait, at that point, right, resistive forces like increases, like air resistance increases as the speed increases, but I don't see how the speed is increasing.
Oh, okay, just now, let me just ask you a question. Initially, the ball is moving so slow, and finally, it is moving so fast, right? Isn't it?
Yeah,
This is what we have agreed, from from the beginning, right?
yeah,
Okay, lah. So when the speed increases, I mean, when the velocity increases, your frictional force increase, isn't it?
yeah.
I mean, this is exactly our point just now, Then this one. Friction increases when velocity gets higher, Isn't it?
Yep, I got it. So basically, when the ball is falling downwards vertically, its velocity it gets faster.
It's moving faster and faster. Okay, like this. If you still can't get it right, later on, you drop something. I'm pretty sure that when the object leaves your hand, it's moving so slow. And when it's about to reach the ground, it'll be moving very fast. Okay?
Okay.
Uh,
Yeah, we can move on. I've already
okay.
marked.
Okay. Have you ever heard of principle of conservation of momentum?
Yeah, I do.
Okay. Would you mind telling me what does principle of conservation of momentum state?
So basically, total initial momentum equals to final momentum.
Mm-hmm. So total initial momentum will be equal to final total momentum, right?
Yeah.
Is there any condition? Is there any condition that we have to follow? Provided that there is no external force. Could you please jot that down? Provided that there is no external force. Then only you can say that total initial momentum is equal to total final momentum. All right?
All right.
Mm-mm. Okay, so now let's talk about this question. Okay. This is actually okay. You know that momentum is mass times velocity, right?
Yes, I do know that.
Okay, very good. So that is why you have to tell me what is the total initial momentum, and you have to tell me what is the total final momentum. All right.
Okay. Yeah, we can move on.
So did you know that kinetic energy is half mv squared?
Yes.
And most importantly, did you know that for elastic collision, right, you are going to conserve both momentum and kinetic energy?
Yeah.
I repeat, for elastic collision, you are going to conserve both momentum and kinetic energy, all right?
All right, I remember.
And what about inelastic collision? Inelastic collision.
I don't think I've learned that before.
Oh, for inelastic collision, hang on. Let me check if I have that document with me now or not. Okay, never mind. For inelastic collision, you also conserve momentum, but you don't conserve kinetic energy.
Oh, I see. Okay.
You also conserve momentum, but you don't conserve kinetic energy anymore.
Okay.
And do you know what is the energy transfer? Like energy transfer, you have to mention, from let's say gravitational potential energy to kinetic energy, that one is called energy transfer. All right.
Yeah, that's
So
right.
did you know that today, when you let
Uh-huh.
go of the compressed spring, of course the compressed spring is going to push both trolleys, away, right?
Yeah, that's right.
So did you know that this is from the elastic potential energy in the spring to the kinetic energy of the trolleys?
Yeah, I do know that. Yeah.
Okay. Just tell me to scroll down when you are ready.
Yeah, sure. I'm attempting it. You've done this question before, huh?
Huh?
You've done this question before, huh?
I mean, if I finish this page, then I can move on.
I mean, like before class, like you've done it before, like off the class period.
With other students, yes.
I see. I always leave my answer in two significant field.
Two or three, both are good, but cannot be more than three. Cannot be four.
Okay. Yeah, we can move on.
Okay. And by the way, did you know that when I label the mass, right, you have to give them different names, Like if you give capital M to P, then of course you are going to give another name for Q. Do you get me?
Yeah, I do get it. Yeah.
Okay, let's talk about number 3. I'm pretty sure that you have heard of specific heat capacity, right?
Yes, definitely.
Could you please give me the definition of specific heat capacity?
Yeah, it's like the amount of energy required to raise the temperature, like by 1 degree Celsius of a substance.
Did you mention 1 kg?
Oh, right. Yeah. Actually, though, I did not, but yeah, forgot to mention that.
Okay, how did we know that? we have to come back to the formula. I believe that you must have seen this equation, right?
Yes, I remember.
So when I try to move it around, C is actually energy divided by mass divided by change in temperature, right?
Yes.
So this is how, I mean, this one, if you translate this into some English sentence, that would be exactly the same sentence that you mentioned just now.
Yeah.
The amount of energy, which is capital E, and then divided by 1 kg of mass. Okay.
Yeah. All
And
right.
then the temperature change is changed by 1 Kelvin. All right.
All right.
You can say that change. By the way, change in temperature 1 degree Celsius equal to 1 Kelvin. Can you believe that? Because
Yeah.
I'm talking about change in temperature. I didn't say that temperature, all right?
Yeah.
If I say that temperature, can you tell me which temperature is higher, 1 Kelvin or 1 degree Celsius? Which one is a higher temperature? Which one is hotter?
One. Actually, I want to know like which is hotter.
Oh, okay. Now look at this. Do you remember what is the coldest? You know what's the coolest? What's the lowest temperature?
Negative 273 degrees Celsius.
Okay. And this is exactly equal to 0 Kelvin. Did you know that?
Yeah.
Okay, so you know the relationship between degrees Celsius and Kelvin, right?
Yeah, sure.
So did you know that 1 degree Celsius is how much? How much Kelvin? Can you tell me? 1 degree Celsius is how much Kelvin?
It's just 1 Kelvin.
Huh? Why? Why do you think 1 degree Celsius is equal to 1 Kelvin?
I thought you said 1 degree Celsius is 1 Kelvin.
That is for change in temperature. Okay, then it seems like you don't really understand this theory. It's okay. It's okay. Now, can you tell me what is your room temperature right now? Right now,
Let's just say 25.
let's just say 27 now. Okay, 27 now. Okay. 27 degrees Celsius, that will be equal to 27 plus 273 Kelvin, which is 300 Kelvin, isn't it?
Yep, that's right. So
Okay.
Kelvin is hotter.
So do you I mean, right now, I'm talking about temperature. This is 27 degrees Celsius, so this is 300 Kelvin, okay?
Okay.
And just now we agreed that the coldest temperature is negative 273 degrees Celsius, which is
Yes.
0 Kelvin, isn't it?
Yes.
Now I have a special request. I would like to know when my temperature is 1 degree Celsius, what is the corresponding temperature in Kelvin?
The 274 Kelvin.
Okay, you're so clever. So now answer my question. 1 degree Celsius is 274 Kelvin, right?
Yes.
So you tell me which temperature is higher?
It's the Kelvin as higher.
Huh? I repeat my question. 1 degree Celsius or 1 Kelvin, which one is a hotter temperature?
It's 1 degree Celsius is hotter.
Yes, 1 degree Celsius is hotter because obviously 274 is greater than 1, right? Isn't it?
Yeah.
So we are talking about temperature here. Are you okay?
Yeah.
Now I'm going to ask you one more question. 28 degrees Celsius is how much Kelvin, please?
It's 302 Kelvin.
302. Huh?
301. 300.
Oh, okay. 301 Kelvin, right?
Yes.
So this one is called temperature scale. Let us discuss how much the temperature has changed. I hope you realize that I stressed the word change a lot, right?
Yeah.
If you change the temperature by 1 degree Celsius, then how much do you change by Kelvin? Also one, right? Isn't it?
Yes, it's also one. Yeah.
So remember this one, I need to stress this enough, This is the change of temperature, all right?
Yeah. Got it.
Not temperature. I said this is change of temperature. Are you okay with that?
Yes.
So that is why for the change in temperature, 1 degree Celsius is equal to 1 Kelvin, all right?
Yep. Got it.
Did you know that delta, the triangle here, means something is going to change?
Yeah, that's right.
Okay. So help me to understand. I said that change in temperature for 1 degree Celsius is equal to 1 Kelvin. But I never mentioned that 1 degree Celsius temperature is the same as 1 Kelvin temperature, I didn't say that.
All right.
All right.
All right. I got it.
Okay, so I think you know this, huh? Do you need to jot anything down? I don't know.
No, it's okay. Got it.
Okay, let's talk about this. Do you know what is the difference between conduction, convection, radiation, please?
Yes, I do.
Okay, tell me what is the difference between them.
Okay, so conduction is basically like a transfer of like thermal energy. It's mainly in solids for conduction.
Solid.
Yes.
Okay, very
But
good.
for convection is mostly in liquid and gases.
Liquid and gas. Do we have a special name to talk about liquid and gas together? Do we
Yeah,
have a
there's a
special
name.
name?
Yeah, there's a name to it, but forgotten what it's
Fluid.
called. Yeah, fluid. Yeah.
Fluid. Is used to describe, it's used to, to talk about liquid and gas, both of them, okay? Because fluid refers to something that can flow around. And obviously,
Yes.
liquid can flow around, gas also can flow around, all right?
Yeah.
Okay, finally, radiation, please.
So basically, it's like the emission or transmission of energy. It's like in the form of waves or particles. It's like through space, or a medium. It needs a medium to travel.
Vacuum, it does not even need a medium.
Okay.
For radiation, you don't even need a medium. So you can just happen in vacuum, all right?
Okay.
Mm-mm.
Vacuum is an empty space, right?
Yes, vacuum is empty space, you're right. Okay, so far so good.
Yep.
All right, let's try out this right now, okay?
All right.
Mm-mm.
Instead of saying like the particles of water move throughout the liquid, can I just say they slide over each other?
Could you repeat?
Like instead of like the water particles move throughout the liquid, can I just say that the water particles they slide over each other?
Mm,
Because they emphasis on the word motion.
can leh. You say that the water particles will slide over each other, but the particles in ice cannot. Yes, you're right.
All right.
Mm-mm. If you have finished question B2, please let me know.
Yeah, I'm done actually.
Okay, now let's talk about convection now, all right?
Sure.
Oh, the ice is floating, isn't it?
Yeah, that's right.
So for the water which is surrounding the ice, the water will get very cold, right?
Yes,
And when you get cold, do you expand or do you contract?
it will contract.
It will contract, right? When you are contracting, your volume is increasing or decreasing?
Volume would decrease.
Okay, volume decrease. Let's talk about density. Can you please tell me what is the definition of density?
Yes, its density is the mass upon volume.
Okay, mass over volume, so good. So when your volume decreases, what happens to your density?
When volume. Wait, do you mind repeating? I was writing something.
Oh, sure, no worries. Volume decreases,
Yeah.
what happens to your density? Will it increase or decrease?
Yeah, density will increase.
Okay. And when your density increase, oh, by the way, do you mind if I
Yeah.
use rho as the symbol for density? Because if you want to change the symbol for small letter d, I'm also okay. You just use any symbol that you like. All right.
Oh, I use like a P basically. It's like
Which
like,
one? This one.
Yeah.
Oh, this one is not called P. This one is called roll.
Okay.
Rolling in the deep. Okay.
All
Okay.
right. Rolling in deep.
Okay.
Beyonce.
No. That's the name of a song. It's okay. We call it roll. Okay, roll. ROL. Okay, ROL. And then
Okay.
when density increases, you are going to sink, isn't it?
Yeah, that's right.
Because for something to float on water, your density has to be smaller than the density of water. All right.
Yeah.
Now, if I throw a stone to the river, oh, the stone will sink. And the reasoning for that is the density of the stone is greater than the density of the water. All right.
Yes, that's right.
Okay, so that's why the cold water will flow down. And in order to replace this empty space, the hot water, can I call it hot or warm? Warm water
Okay.
will go up. All right.
Okay.
So this is like a cycle, right? This is like a cycle, right? I mean, the traffic is like this, The traffic is like this, Are you okay?
Yes.
This traffic, we can call that convection current. Convection current. It looks like a current, isn't it? There's a flow of something,
Yep.
Convection of current, okay? And this is, what is the name of this process? Is it conduction, convection, or radiation?
It's convection. It's convection.
Okay. Okay, you can try to solve this now.
Okay. Yeah, we can move on.
Okay. Now, let's talk about this. When the temperature of water is very high, I can imagine all the water particles are vibrating so hard, right? Isn't it? They are like moving
Yeah,
so
right.
fast. Now, when your temperature drops, what happens to your energy?
Your internal energy of the water will decrease.
And what about kinetic energy as well?
Yes, it will decrease too.
Now I'm going to ask you this. Did you
Okay.
know that internal energy is referring to both potential energy and also kinetic energy? Did you know that?
Yeah, I do.
Okay, let's talk about kinetic energy. When you are moving very fast or when you are vibrating very fast, then your kinetic energy is very high, isn't it?
Yes, that's right.
So how to know what happens to your potential energy? Like how do I know that? Now I'm going to draw you some diagram. Okay. Okay, in your diagram on your left, okay, it's like this. Okay, so this is three independent diagrams, all right?
Yep. Okay.
Okay, so imagine that you are the same man here. Which man has the highest gravitational potential energy?
It's C.
Okay, how did you know that?
It has
Because
because it has the greatest height.
So do you agree that when your distance between two objects gets larger, your GBE is larger? Agree?
Yeah, I agree.
Now let's talk about solid, liquid, and gas. All right. I think you are able to know what I'm doing here, right? I'm drawing out the
Yeah,
solid, liquid, gas thing.
yeah.
Which one has the highest potential energy? Can you tell me? Is it solid or liquid or gas? Which one will have the highest potential energy?
I can.
Sorry.
Uh, wait. Does it relate to the error ratio separation? Like
Yes. It is related to the separation. Yes, you're right.
So I would say C has the highest.
Yes, gas will always have the highest potential energy compared to the other two states. Are you okay?
Yeah. Okay.
Okay, so now you get me, eh?
Yeah, I do.
Okay. So now, just a summary. If your temperature is higher, your kinetic energy is higher. Are you okay?
Yeah, agree.
The higher the temperature, the higher the kinetic energy. Now, if you ask me about potential energy, we will have to look at solid, liquid, or gas. And you know that gas will have the highest potential energy, all right?
Yeah.
Okay. You can answer this question now.
Okay. Okay, we can move on.
Have you learned about lenses?
Yeah. Yeah, I did.
Okay. So now let's talk about this lens. Okay, this is called convex lens, right? Isn't it?
Yes.
Does it have another name? Does
Is
it
it
have
just
another name?
diverging lens?
No. This is called converging lens, dear.
Oh, I thought you meant like another one. But okay, yeah.
Yeah. I'm not talking about the another lens. I'm talking about the same lens but with another name.
Okay.
Okay.
Okay. Yeah.
Okay. So now let's talk about this. If you have parallel lights, I'm pretty sure that they will converge to a single point, right?
Yes, they would.
And what is the name of that point?
Focal point?
All right. So what is the distance between focal point and the lens? Focal length, right? So we have to be sure focal point is about that point. Focal length is the distance between the focal point and the lens, all right?
All right.
And I'm so happy that you know the another one is called diverging lens, isn't it?
Yeah, that's right.
And when you have some lights, you know that the light is going to diverge away, all right? It's going to diverge away. And it seems like, okay, forgive me for my very bad drawing here. You are going to use a ruler to draw that, right?
All right.
So it seems like for parallel lights, the lights will behave like it is going to diverge from a point, and we also call that focal point, all right?
All right.
And by the same reasoning, the distance between focal point and the lens will be?
The focal length.
Okay. All right, so now you can do this.
Yeah, we can move on.
Okay. Did you know that when you're using magnifying glass, your object has to be really, really, really close to the lens, isn't it?
I see. Yeah.
Like imagine when I'm taking a magnifying glass to, let's say, to look at the words in dictionary. I suppose the magnifying glass is quite close to the dictionary, right?
Yep.
And then my eyes is actually quite far away from the magnifying glass, all right?
All right.
Okay. Now I'm going to ask you, did you know the definition of a real image?
It's like
What?
real image. Basically, it's like it's formed where like the rays like where the rays of light, they will converge like after it passed through the lens, and that like real images are like always inverted to the object,
Very good, very good.
and
And
then
one
they
more.
can be like projected on the screen. Yeah.
Yes, you're so clever. The real image can be projected onto any screen, but the virtual image cannot. All right.
Yeah. Yeah.
So when you look at yourself in the mirror,
Okay.
do you think your own image is real or virtual?
I think it's virtual. So it's
Because you
yeah.
yeah, you cannot project what you see yourself in the mirror, right, onto any screen, all right?
Yeah, true.
Okay. Okay, so check that out. Do you get upright and virtual here?
Wait, I have a question like for
Mm-hmm,
A2,
mm-hmm.
like where they ask you to like put a point X, like why does it have to be close to the lens, like near to the lens?
Oh, this is actually what we agree. For magnifying glass, you are going to put your object so close to the magnifying glass, you know. And then,
Yeah.
then you see, this is like let's say this is like a small thing, a very small end. Okay, small thing.
Okay.
You are using your magnifying glass to look at the ends. So you are going to put the ends so close to the lens, right? But then your
Oh, okay.
eyes, you are not going to put your eyes so close to the lens, right? Isn't it?
Yeah.
Hmm.
Wait, but actually, I would put my eye close to the lens though.
If you put your eyes so close, right, I'm pretty sure that you cannot see the ends clearly.
Oh yeah, yeah, true.
Mm.
Okay. Wait, focal length is like the distance between the lens and the object. Is that the definition?
Yes, focal length is the distance between focal point and the lens.
Okay.
Mm.
Wait, how do you know that this is virtual and upright? Like, how do you know this is converging lens?
Oh, okay. Now, let's look at this. You are using your magnifying glass, right?
Yeah.
So I'm pretty sure that the image will be much, much, much bigger than the object, isn't it?
Yes.
And so you asked me a very good question. I'm going to show you some images. Hang on,
Okay.
but at the same time, you can try to do this first. I'm going to show you something first, all right?
Okay.
Okay, let's talk about this, all right?
Okay.
Okay, so today, this page is all about convex lens. Are you okay?
Yeah.
Let's talk about this. When your object is so far away, the image will be real, inverted, diminished. Are you okay?
Yeah, okay, I understand.
And when your object is at 2 times the focal length, your image will be real, inverted, and same size as the object. Are you okay?
I see. Okay.
So now I'm giving you some time. You have a look at this. And at the same time, I'm going to draw out a table that I always ask my student to, memorize. All right.
Okay.
Okay, so first and foremost, please ensure that for all the ray diagrams, minimum you can draw me 2 light rays. Maximum you can draw me 3 light rays. Are you okay?
Yeah, okay.
For example, I'm going to show you this. Actually, I could have drawn one more light ray here, and you know what? It will still get me the image. Are you okay?
Yeah, I'm okay.
Oh, by the way, I think you know how to draw this rays diagram, right? If you don't know how to draw, please let me know. All right.
All right, sure. Yeah, I know how to
Like
draw.
you know why it's like horizontal and then suddenly going to the focal point, right? Isn't it?
I mean, I don't
And
really know why it's horizontal, but like I know how it like looks like.
yes. And you know that when the light ray is passing through the center of the lens, it will simply go through that in a straight line, isn't it?
Yeah, that's right.
And then when you have passed through the focal point, then you are going to move horizontally later on, all right?
Yeah, okay.
And you know that most importantly, the point where all the light rays converge together is exactly where the image will be.
All right, okay.
So for example, this one, I could also draw this. Like there's a light ray passing through the center of the lens and it does not change the direction. And please don't forget to give it an arrow. Arrow is quite
Okay.
important. All right.
All right. Yeah.
The light will always go from object to image, not the other way around. All right.
All right, sure.
So for this one, actually, I could also do the same here, but unfortunately, it seems like the lens is too short for me today. Okay.
I see. Okay.
Okay. But anyway, yeah, it should look like this. Okay.
Okay. Yeah.
Okay. I should be more accurate now. Okay. So now, like I said, for all the ray diagrams, at least you can draw me 2 light rays. At most, you can draw me 3 light rays. All right.
All right. Yeah.
And unfortunately, there are some diagrams where I really cannot add on one more line for you. So for example, you look at these 2 diagrams, I really can't add one more ray for you. So that's why you only can draw 2 light rays here.
Okay. Yeah.
Can I?
Yeah. Can.
And did you know that, I think you know this already, because just now when I asked you what is a real image, you told me that the real image is like the light rays really converge together to form that image, all right?
Yeah, that's right.
But for virtual image, to be honest, the light ray does not even travel through there. Okay,
Oh, I
so
see.
the image is actually fake, because
I see.
because if you ask me why did we put dotted line, right? Dotted line means the light ray does not even travel through here. All right.
Oh, I see. Okay.
But you know what? Humans are stupid. When humans' eyes are here, we believe that the image is here because we believe that. Okay, we thought the light ray comes from there, but in actual fact, it doesn't. All right.
Oh, I see. Okay, I
So
got
that's
it.
why virtual image is something like we call it fake fake image. It does not even exist, but our brain is so stupid. We tell ourselves that the image is there, but actually it's not. All right.
I see. Okay, I understand.
And
Yeah.
the thing is, normally I will ask my student to memorize this table, right before they go to their exam. So help me to understand that this is only for convex lens. Are you okay?
Yeah.
You can check it out. See, you know what is capital R, capital I, capital D, SS or
Okay.
not?
R is real, V is virtual.
R is real, V is virtual, and then
So I is image, U is upright.
no, I is inverted, U is upright.
Okay. What's
Mhm.
SS?
Same
Same size.
size. Yeah, the image is the same size as the object.
Then M is magnified. D
Yes,
diminished.
yes, so clever. Magnified meaning that image is bigger than object.
Oh, okay. Oh,
Diminish,
what we did just now.
diminish means the image is smaller than the object.
Okay.
So anyway, help me to memorize this table, then you are able to answer the question just now, all right?
Okay.
And by the way, for magnifying glass, it's like this, this one.
Uh-huh.
This is actually magnifying glass, like this one, the last one, magnifying glass.
Okay.
So yeah, so that is why you can imagine, like what we agreed just now, we put our eyes so far away from the lens, but we put the object so close to the lens, isn't it?
Yeah, that's right.
Mm-hmm. And let me jot it down here. Dotted line means the light does not travel here.
Is it okay if I can use the washroom real quick?
Oh, sure. I can wait for you.
I'll be back. Okay, yeah, I'm back.
Okay. And I'm pretty sure that actually okay, wait a minute. So this page is all about convex lens, all right?
Yeah, okay.
And I suppose you are much younger than me, and I suppose that this is the lens that you are wearing now, isn't it? I mean,
Yeah.
you now look at your glasses, is it thinner at the center and thicker at the ends?
Yeah.
And now can I ask you a little flavor? Like a little favor, you take off your glasses and then you put your glasses like maybe 10 cm in front of your eyes and you try to look at the world through the lens of your glasses, all right?
Yeah, I'm doing it right now.
It seems like the whole world is squeezed into that lens, right?
Yeah, white.
And obviously it's not upside down, right? You don't see the
Yes,
word
no.
upside down.
Yeah,
Okay.
no.
So, okay, now our conclusion is for concave lens, which is the lens that you are wearing right now, your image is always diminished virtual upright. Okay? It will always be like that.
Okay.
So if you ask me, why is it so complicated? Just now, if you look at convex lens, right? When your object distance changes, they will be the characteristics of image will also change accordingly. But for concave lens, I don't really care where the object is. Your image is always to be VUD, virtual upright diminished VUD. Okay?
Yeah, okay.
So I hope you know how to draw the, ray diagrams, all right?
Yeah, sure.
Okay. So can I go back to the question just now?
Yep, you can.
So for magnifying glass, I hope you remember that is magnified virtual upright. So I hope this answer your question here, all right?
Yep. Okay. Yeah, we can move on to the next one.
Okay, let's talk about reflective index. When it comes to reflective index, how many formulas or equations that you can tell me that you have learned in IGCSE syllabus?
I think it's that n equals to 1 over sine c. The first one.
Good job, good job. And the C here is referring to?
The speed of light.
No.
Critical.
Sine C, sine angle. So that is referring to critical angle. The one that
Okay.
you talk about is this one, the speed of light in vacuum, all right?
All right.
And what is this small letter V?
Velocity
Velocity of what?
of a medium.
Okay, speed of light in medium, okay?
Yeah.
They are all referring to the speed of light, but in different cases, all right?
Okay.
And I believe there's one more equation. There's one more equation involving reflective index. What is that?
Kind of forgot, actually.
Okay, so if we have two different mediums, this is N1, this is N2. Let's say the light travels like this, okay? And the light travels like this. Did you know that our angle is always measured from the normal line?
Yeah, that's right.
By the way, did you know that this dotted line is called normal line?
It's n equals to sine I over sine r.
Ah, very good. And that is exactly the one that you learn in your textbook. And to be honest, I don't really like that. I prefer this one. But they are the same guy. Right?
Oh, I see.
This one is the one that I prefer. But if you want to stick with the what? Come again, what's the formula again just now?
Oh, yeah, n equals to sine I over sine r.
Okay. Okay, you can also accept this, all right?
Okay.
But I want to tell you, actually, both of them are the same. Okay?
Okay, yeah, sure.
The reason why I don't really like this is because when you use this equation, by default, one of the medium must be air or
I
vacuum.
see.
Okay?
Okay.
Because only when you are air or vacuum, then one of the one of the reflective indices will be 0. Because did you know that air or medium has the reflective index of 1?
I didn't know that.
So how many to remember? For air or vacuum, the reflective index is equal to 1. Are you okay?
Yeah. Okay.
So I need to stress again. You can still stick with this because you are still in IGCSE syllabus. So this equation is very fine. It works perfectly. All right.
All right.
But
Okay.
you should understand that the underlying condition, whenever you use n equal to sine I over sine r, it means that one of the medium must be air, or one of the medium must be vacuum. Is like that. All right.
All right. Okay.
Mm.
Got it.
My version of this is how do I say? I believe this is a bit more practical because you know n1 and n2 can have any value. All right.
All right. Okay.
Oh, speaking of which, did you know that refractive index will always have a value of greater than 1?
No, I didn't
Uh,
know that.
Reflective index must be either 1 or greater than 1. I won't be
Okay.
able to see anything like reflective index is 0 point something. No, it should
All right.
it does not exist,
All right.
Mm. Okay, so once again, I need to remind students, whenever you see reflective index, I'm pretty sure that there are only 3 equations for you. Okay?
Okay. Yeah.
And the
Okay.
thing to be very careful about is the small letter c. Sometimes it's the critical angle, sometimes it's the speed of light in vacuum.
All right.
Well, it just so happens that they share the same name, all right?
Yeah. Okay.
By the way, what's your name again? Trish, is it Trish?
Yeah. 3.
I'm pretty sure that in the world there will be at least another student with the same name as yours, all right?
Yeah.
So this is exactly what happened here. They just happen to share the same symbol, small letter c, all right?
All right.
Mm-mm. Okay, so finish this page, then let me know.
Yeah. Already finished.
Okay. Yeah, this one is how we draw the light light ray diagrams for magnifying glass. All right.
All right. Okay.
Yeah, your object is so close to the lens. Your eyes are so far away from the lens on the
Yeah.
other side. Okay.
Okay. Yeah. Got it.
Okay. Have a look at this.
Do you have another class after this?
No, but I have another class starting from 4:30 later on.
Okay.
So I can give you like extra 5 or 10 minutes if you need that.
Because I want to like discuss the last few questions because it's like what
Okay.
I'm learning. Yeah.
Which one? Tell me.
Like, remember about like the nuclear physics and like the transformer and all.
Yes, please.
Yeah. Yeah, that's like what we learned like last week in school basically. So I just want to like hear like more from you.
Oh, that means you want me to
Yeah.
go through some notes with you, is it?
Oh no, like do past papers.
Okay. Transformer. Wait a minute. You want transformer and what again? Nuclear physics.
Yeah.
Okay. Or maybe you can jump to question 8 first. All right.
Yeah, sure. Also can. Yeah.
And meanwhile, let me search for transformer question.
Will you send this on my WhatsApp?
Of course, I will send you everything.
Okay.
I'm pretty sure you have heard of alpha radiation, beta
Yeah.
radiation, and also gamma, right? Can you tell me
Yes.
what is alpha actually? What is an alpha particle?
Alpha particle. They have like a positive one, no, there are positive two charge actually. It's like, yeah.
Positive two charges, and then
And
did
I
you?
remember it has like high ionization and like
Mm-mm.
it can easily be stopped like by like a piece like a thin sheet of paper. So it's not easily penetrated.
Very good. Very good. So basically, alpha particle is just a helium nucleus, all right?
Yeah, okay.
I need to mention this, alpha particle, helium nucleus, because I don't want students to tell me there are two electrons here. Obviously, they are not. Okay?
Okay.
You only have two proton, two neutron, no electron. Okay? That is why just now we mentioned that the charge is plus two. Plus two, okay? Plus 2e.
That's okay.
At the same time, I also want to ask you, what is a beta particle actually?
It's an electron.
Okay, fast-moving electron, all right?
Yeah, okay.
At the same time, what is gamma? I think you must have learned it in the chapter of wave, the electromagnetic spectrum.
Yeah, it's an electromagnetic wave.
Very good. Electromagnetic wave or electromagnetic radiation. So it does not have any mass, right?
Yeah, it doesn't.
Does it have any charge?
No, it's zero.
Okay. Okay, so now let's talk about this. Did you know that for fast-moving electron, the number must be 0 and -1?
Yeah, I know.
And a quick question. What is this number on top? What is this number at the bottom?
Top is nuclear number, bottom is atomic number.
Okay, very good. The top one is nucleon number. The bottom one is atomic number, right?
Yes.
Do they have some, synonym? Synonym.
Have what synonym? Oh, like mass number and then quantum.
Mass number. Very good. And proton number, okay?
Yeah, okay.
Okay. And I think you know okay, by the way, I think you know that for fast-moving electron, it must be 0 and -1, right?
Yes.
Just like for alpha particle, it must be 4 and 2.
Okay.
And now your only job is to make sure that this number equal to this number plus this number, and the same goes to purple one, okay?
Okay, but why does it have to be like the same, like both sides?
Because you are going to conserve the nuclear number, you are going to conserve the proton number. You cannot tell me like in any reaction, right? Suddenly suddenly one of the nuclear number goes missing. I mean, it can't be that way, right? All right.
Okay, I got it.
I mean, people or atom can't just vanish into thin air, for no reason, right?
Yeah, true.
Okay.
But what happens if your nuclear number that go missing?
Repeat, if you have nuclear number that goes missing,
Yeah, what happened?
that means your reaction is not even correct in the first place.
Okay, yeah, okay.
Because this is what we agree. Just like when we learn conservation of energy, if you suddenly ask me like, teacher, what happens when some of the energy goes missing? Well, it must be the case that we have done some mistake. Okay, that means we have basically ignored some possible ways that our energy can be converted into some other forms. But I can trust. I can tell you that we have to trust that energy conservation is always valid. All right.
Okay, yeah. Actually, why like when there's too many neutrons, like why does it cause a nucleus to be unstable?
Okay, well, in a nucleus, we have both neutrons and protons, right?
Yeah.
If either one, I mean either neutron or proton, if one of them gets too large, then you are not balanced anymore, you know.
I see. Okay.
So if either one, let's say either proton is too many or neutron is too many, neither one, right? I mean either one will result in very unstable nucleus. So eventually they will split. But if you ask me why, I can tell you later on if you are still interested in physics, we have something like the region of stability for nucleus.
Oh, I see. Okay.
Maybe I can understand. I think I can understand your question. You know, because when I was young, I used to think that, like, you know, when protons are too many, I can understand that protons they try to repel each other. So that's
Yeah.
why the nucleus is not stable. But I can't really understand why when the neutrons, you know, neutron is basically neutral, right? So when
Yeah.
neutrons get too many, I don't think they will cause much disruption. But this is not the case. This is not the case. They must reach a, how do I say? The neutron and proton must have to reach a certain ratio. Then only the nucleus is quite stable. All right.
Oh, I see. Okay.
And in fact, later on, this is something that you are going to learn in A level. You are going to learn something like this, you know. You know that the most stable element in the world is actually iron, Fe, you know, Fe, ferrum, all right?
Okay.
But okay, it's okay. This is something that we are going to learn later on in the future. So I will just skip your question first. Okay?
Okay.
But you'll ask me a really, really lovely question, I can tell you.
I see. Okay. Actually, my physics teacher, like, he didn't really teach like really well, to be honest. But like, do you mind, like, is there any half-life question? Because I'm a bit confused with half.
First and foremost, normally I don't really comment about other teachers. I really believe that all the teachers have their own strength and weakness. I also have my own weakness, just that you haven't discovered yet.
Okay, I
Okay,
understand.
later I will share you some questions about the half-life and things like that. Don't worry.
Okay. Yeah, we can move on.
Okay. Okay, this one is about Fleming left-hand rule. I'm not sure if you have mastered this or not. Okay, Fleming left-hand rule.
Oh, I heard of it, but sometimes it's, I don't know, a bit confusing.
Okay, now you take out your left hand. Left hand.
Yeah. Okay.
You tell me what is represented by your thumb and then your index finger and then your, you know, middle finger.
Yeah. So thumb is basically direction of force, index is magnetic field, and then middle finger is current.
I love your answers, but for your thumb, when you mention thumb is about force, right? Could you be more specific? Like you have to tell me that it's actually magnetic force, all right?
Oh, okay. All right.
Mm. And one more thing is, let's say there's a proton moving to the right. Did you know that it means current is also going to the right? Because direction of electric current is the same as the motion of, you know, any positive particle.
Oh, I see. I didn't know actually.
And then this one, beta, I think you know beta minus is talking about electron, right? Free moving electron.
Yeah.
This is what we mentioned just now. So
Yes.
when your electron is going to the right, that means your electric current is going to the left.
Oh, okay.
I think you must know this because when there's a battery here, we are going to tell student that, you know, the current is going like this, but your electron flow is like this. So that is
Yeah,
why electron flow and current will be, you know, in opposite directions. Okay.
I see. Okay.
Okay, try to use your left hand to get the direction of the magnetic force is going downwards. If you don't get that, you can tell me. I'm going to, I don't know, I'm going to show you how to use this.
Okay. Can you explain for question like for the beta part, like the diagram, like what's the deflected?
Okay, let's talk about gamma first. Gamma is quite easy. You know that gamma must be moving in a straight line only, right?
Yeah, because it has no charge.
Because it has no charge, so there will be no magnetic force. Okay?
Yeah.
Okay, now let's talk about gamma. Sorry, beta. By using Fleming left-hand rule, I know that beta is going from left to right. So I can imagine the current is going from right to left. And did you know that it means the magnetic field is going into the page? So that's why you can see a cross here.
Yeah, that's right.
And so I'm going to use my Fleming left-hand rule, okay? Fleming left-hand rule to check that, okay? To check that my direction of magnetic force is going downwards, all right?
Okay.
So when the magnetic force is going downwards, I can say that the electron will move down. I mean, you can imagine there's a force, there's a force trying to, pull the electrons down. Okay, so yeah, this is it. Okay.
Okay.
And okay, wait a minute. Having said that, I'm assuming that you can apply Fleming left-hand rule to detect that the direction of the magnetic force is really going downwards, right? Is it? Because if you fail to use a Fleming left-hand rule to show that magnetic force is going downwards, then I'm gonna show you this image. First and foremost, just to be sure, we are using our left hand, right?
Yeah, that's right.
Your index finger is pointing onto the screen, like this, pointing to the screen.
That's right.
Because magnetic flux density is going into the screen.
Yeah.
And then my middle finger, this is my middle finger, is going to the left because my current is going to the left, all right?
All right, yeah.
So here I will pay my attention to my thumb. My thumb is pointing downwards. So that's why I know that the magnetic force is downwards, all right?
All right.
So this is Fleming left-hand rule, all right?
Oh, so that's why it's deflected downwards for the beta.
Yes.
So like when there's a downward force, the deflection like it will go down.
Yes.
Oh, okay.
I mean, you imagine when I push you to the left, of course you are going to the left a bit more. I mean, whatever the force is exerting on you, you are like following that direction, okay? I mean, you imagine there's a force like push you there, if I push you to the left, of course you're going to the left, right?
Yeah.
Okay.
Yeah. Okay, yeah, I understand. You can move on.
Okay. So you haven't learned space physics yet, is it? Or maybe you haven't finished that chapter?
I haven't finished that chapter actually. Yeah.
Okay, no worries. Okay, so let's quickly talk about the one that you asked me, transformer, okay? Transformer.
Yeah, sure.
Okay, just to let me ask you. Did you know that? This one is actually soft iron.
Yeah, I know.
The body is soft iron.
Yeah.
And did you know that the wire is, let's say, copper wire? Copper.
Yeah.
Can you actually replace iron with, let's say, steel? Can or not?
No, you can't.
Cannot, because steel is a hard magnetic material. Soft iron is a soft magnetic material, all right?
All right, yeah.
And have you ever learned this equation yet?
Oh, yeah, I did.
What is capital N? What is capital V?
N is like number of turns, and V is the voltage.
What is P? What is S?
Yeah, P is primary coil, secondary coil.
Okay. And did you know that all the transformer will be, I mean, this equation is valid for all the transformers in the world?
Yeah.
Like, I don't care you are step out or step down transformer. I don't care you are ideal or non-ideal transformer. As long as you are a transformer, you can apply this, all right?
All right, okay.
And there is an equation.
Wait, I have a question.
Yes, please.
Yeah, but like, what if it says like, like, what if it's not 100% efficient? Can you still use that equation like the just now?
Oh, this one, no?
Yeah, can you
Valid
still
all
use
the
it if
time.
it's not 100% efficient?
Like I said, this equation only, NP over NS equal to VP over VS, valid all the time. I don't care you are how many percent efficient or what. I don't care.
Oh, okay.
Okay.
Yeah.
As long as you are a transformer, then you are good to use this.
Okay.
And now, only when you say this is 100% efficient,
Okay.
then only I can say that find the power input is equal to the power output. So VPIP equal to VSIS. Okay.
Okay. Yeah.
This is only valid when you are 100% efficient, or we can say that the transformer is ideal. All right.
All right. Sure.
And of course, to answer your question, just now you asked me like what if it's not like 100% efficient, right?
Yeah.
Then I'm going to ask you, what is the formula of efficiency that you have learned? Could you please tell me? Thank you.
Yeah, it's like useful power output over total power input.
Okay. Now, would you mind giving me some, give me the equation in detail? Can I have the useful power output formula? Can I also have the total power input formula, please?
Yeah, it's like efficiency over total power input if you want to find power output.
No. Actually, I was asking you about this. The useful power output is VSIS. The total power input is VPIP. This is what I mean.
Oh, okay.
Yeah, this is what I mean.
Yeah. All right.
Can I?
Yeah.
So that is why in some textbook, they are going to put this guy equal to IS over IP. Are you okay?
Yeah. Okay.
Remember this green color, is only valid for 100% efficiency,
Okay. Yeah.
If you are not 100% efficiency, I mean, if you are not 100% efficient, then don't use this, okay?
Okay. Yeah.
Okay. So maybe I can give you 1 minute. You can quickly have a look at this page. I'm going to send you this later on, all right?
Okay.
So far so good?
Yeah. But like for the last part, not last part, actually is the first question actually.
Oh, yes.
Yeah, like why can't I do 240 over 6 times 8,000? Because I don't get the
This is mathematic question. Whoa. Okay. Okay, you say that you want to say that 240 divided by 6 and then multiply by 8,000, right?
Yeah.
This is a completely wrong mathematical execution. Okay, so anyway, let me show you this. 8 divided by 2 equal to 4. Do you agree?
Yes.
You agree, You agree this is a good mathematical, is a mathematical equation that makes sense, okay?
Yes.
Can I actually interchange these two positions, can or not?
No, yeah, you can.
We can. We can actually, you know, how do I say, interchange these two variables. Can I? These two numbers, okay?
Yeah, sure.
Okay. So one more thing is like this. Let's say how do I say? 18 divided by 9 is equal to, okay, divided by 3 is 6. Divided by 3 is 3. Agree? 18 divided by 9, is it equal to 6 over 3? Yes or no?
Yeah, it is.
Yeah, it's the same. Very good. I mean, it's a mathematical equation that makes sense, right?
Yes.
So we have to remember that long time ago, our math teacher taught us something like butterfly method. So 18 times 3 equal to 9 times 6, isn't it?
Yep, that's right.
Okay. So let's come here. Here I advise you to use your butterfly method. Okay. So 2400 NS equal to 6 times 8,000, which will basically give you NS is equal to 6 times 8,000 divided by 240. Okay.
All right, I got it. Thanks.
Another way to solve this is like, for example, 240 divided by 6 will return 40. So basically for me, right, 8,000 divided by NS equal to 40. I remember that these two numbers can, interchange the location. 8,000 over 40 will be 200. This is another possible way.
Okay, yeah, I got it.
So I don't care which way you are using. Just don't tell me the same thing. 240 over 6 times 8,000 cannot lah. Cannot. Okay, it cannot be like that.
Okay. Yeah, we can move on.
Okay, and finally, I want to tell you just now, if you still remember, just now when I asked you for Fleming left hand rule, right, and then you told me like your thumb is like force, and then I said that I'm not really satisfied with the answer force, right?
Yeah, it's
I
magnetic.
said that yes, it is magnetic force, and why lah? Why do I mean, why am I so picky? Okay, it's like this there. So for Fleming left-hand rule, please understand that for Fleming left-hand rule, your thumb is the magnetic force. And then for Fleming right-hand rule, your thumb is the mechanical force. Are you okay?
Okay,
Did you know
yeah.
what mechanical force? Mechanical force is like if I'm now going to push you, I push you with my hands. That's called mechanical force. Mechanics, all right?
All right.
If I play tennis, I use my hand, I use my hand to let's say to hold the racket, and then I use my racket to how do I say, to hit the tennis ball. This is called mechanical force.
All right. Okay.
Like manual force lah, okay, manual force, all right?
Okay.
And one more thing I really care about is just now when you say current, I'm very fine because this is the current from the power source, okay?
Yeah.
For Fleming left-hand rule. But for Fleming right-hand rule, this is not the current coming from the power source anymore, This is the induced current. This is the current that you have produced without any power source, okay?
Okay.
Have you ever heard of induced current, by the way? Induced.
Yeah, I do.
For me, induced is like produced, okay? Produce the current produced by you, by your own effort. Okay.
When do you use right hand?
Sorry, come again.
Oh, actually, you've already written it on the screen.
When you, sorry, come again. What's your question, sir? I didn't hear you clearly. Sorry.
Oh no, because I like, when do you use Fleming's right hand rule? But then like on your screen it says AC generator. So.
Yes. Because you want to produce your own. Okay, like this. Whenever you want to produce your own electricity, remember this. Okay. One day. Can you imagine that you are going to live in the world where we are not going to give you the electricity anymore?
I can't imagine.
Like dear households, the government is not going to give you the the electricity anymore. So take care. Okay, generate your own electricity then. Thank you. Okay, so if one day you have to produce your own electricity, have you learned this? Like when let's say you have a spring, and
Oh, the
then you have
solenoid.
solenoid, and then you want to push the magnet.
Oh yeah,
You are
Lens bulb.
using your hand. You are using your mechanical force. You are using your hand to stuff the
Oh,
magnet
yeah.
inside. You know.
Yeah.
Then
Yeah.
suddenly you have some current here, right? Detected by the galvanometer here, right?
Yeah, that's right.
This is galvanometer or ammeter, I don't care lah. All right.
Okay.
So you are producing your own electricity, right? Isn't it?
Yep, that's right.
So normally we are using Fleming right hand rule to check the direction of the induced current. Please
see.
understand
Okay.
that. Please understand that you are going to apply Fleming right hand rule whenever you are producing your own current. Okay?
Okay, I got
Or
it.
maybe for the sake of exam, I can tell you when there is no battery. When there's no battery provided. How do I say? No power source. Okay.
Okay.
Like whenever there's no power source, you know that you are going to be responsible for your own current now. So yeah, you are going to use Fleming right hand rule. And did you know that AC generator is the one that we are going to use to generate AC current?
Yep, I know.
Do you know what does AC stand for?
Yeah, alternating current.
Very clever. Okay.
Yeah.
On the left hand side, when you are trying to use Fleming left hand rule, right? Normally when you please remember that there will be some current, and then the current is actually from your power source. Okay.
All right. Okay.
That means there must be some power source to make sure the charges are already moving.
Yeah. Okay.
Then I repeat, there must be some, how do I say? There must be some hidden power source to ensure that your particles are already moving. For example, this one. Just now, we agree that the particle is already moving from left to right, right?
Yeah, that's right.
We are not going to argue why the particles are moving. Why are they going from left to right? What gives them the force so that they can move from left to right? We are not going to talk about that, right? I mean, it's none of our business, right?
Yeah, true.
We already know that the charges are moving, that's it. And when you already have charges which are moving, do you know that moving charges means there will be some current?
Yeah, I know that.
Meaning that the current has been provided for you, right? You are not going to generate your own current anymore, right? Isn't it?
Yes.
Then only we use Fleming left hand rule.
Okay.
Can I?
Yeah, can.
So one more. Just remember, okay? DC motor, Fleming left hand rule. AC generator, Fleming right hand rule. Okay.
Okay.
And then DC motor is like motor, right? Like for example, I have my, let's say, fan right now. Okay, I'm going to turn on the ceiling fan because I feel so hot right now. So I'm basically wasting my electrical energy so that the fan can rotate to give me the mechanical energy, right?
Yeah, that's right.
Because I'm telling the fan, right, hello, please use electricity that I provided for you, and you are going to make sure the air molecules are moving so that I can feel colder. Okay.
Okay. Yeah, I got
But
it.
AC generator is like what, can you give me some slaves, to rotate something so that I can get my electrical energy? Okay.
Oh, okay. Yeah, sure.
Because there's no free lunch in the world, right? You want to produce electrical energy, of course, you need to give me some mechanical energy first, all right? Like you
Yeah,
need to
sure.
ask people, you need to ask some slaves, some people to help me to rotate the turbine, rotate, keep on rotating. Yeah. The moment you stop, then it's the moment I stop getting some electricity, all right?
Yeah, okay.
Okay, so actually, I have another student coming right now, so I think I need to leave first,
Yeah.
all right? Okay.
Okay,
So
yeah, sure.
see you next time. Okay, bye bye.
Yeah, bye. Take care.
Take care.